Good afternoon, everyone. I'm Jamie Jean, and today I'll be discussing a PhD dissertation paper by Irene Giacomelli. In this PowerPoint, I will be discussing the applications of secret sharing schemes to cryptographic protocol designs. I'll be focusing on secret sharing schemes that can be used to design commitment schemes in the universal composable security model. This paper also shows how to use secret sharing schemes to design commitment schemes that have asymptotically optimal computational complexity and homomorphic properties. It also talks about their efficiencies. The term secret sharing schemes refers to a method for splitting a secret in several pieces, such that the original secret can be reconstructed only when a sufficient number of pieces are combined together. Although it was originally introduced to solve the problem of secure data storage, it is now used as building blocks of cryptographic protocols that implement different and more general tasks such as multi-party computation protocols and electronic voting systems. The goal of this dissertation was to study and develop applications of secret sharing schemes and cryptographic protocol designs. This includes, on one hand, identifying cryptographic primitives whose existing constructions can be improved by the use of secret sharing schemes, and on the other hand, it involves designing new suitable secret sharing schemes that present the properties required by the specific cryptographic applications. In this paper, Irene spoke about three different projects, but the one I'll be focusing on is the mini commit project. The mini commit project is a commitment scheme that is a two-party protocol that can be thought of as a digital equivalent of a secure box. It allows the prover to commit to a secret by putting it into a lockbox and giving it to a verifier. Due to the box being locked, the verifier does not learn the secret at commitment time. Although the prover can later choose to give the verifier the key to the box to let him learn the secret. And since the prover gave the box away, he can't change his mind about the secret after commitment time. The main goal of this project is constructing efficient commitment schemes with strong security properties, especially now that secret sharing schemes are used to design commitment with homomorphic properties and low computation complexity in the universal composable security model. As concerns the design of new secret sharing schemes and motivated by the application, this paper focuses mainly on the following two aspects: efficiency and security. Efficiency, the main goal is providing explicit constructions of secret sharing schemes with good properties and low computation complexity. The focus was in secret sharing schemes with low communication complexity. For a specific scheme, the relation between the secret length and the total amount of data produced and sent in the sharing phase was studied. In security, a secret sharing scheme assures the security against an attacker who tries to guess the original secret by having access to only a few shares. In the application of homomorphic commitment, it is assured that the sharing phase is executed by a dealer, which after the computation privately sends the computed shares to other parties. If the dealer is corrupted, how can the parties receiving the shares verify that the sharing phase was done correctly? That was answered in this paper. Besides this simple security property, which is provided by any secret sharing schemes, by definition, there are others that can be required in different settings. For efficiency, if a secret sharing scheme is used as part of a construction realizing another primitive, the efficiency of the final construction can be influenced by the efficiency of the secret sharing scheme used. To evaluate the performance of secret sharing scheme LSSS, the paper looks at communication efficiency and computational efficiency. In communication efficiency, we're to find the rate, the quotient of the length of the message M over the length of the shared vector. That is, if the shared vector finite field to the power of k mapped to the finite field L times the power of n. we have that the rate is the positive real numbers given by rho equals k divided by n times L. It is known that if the scheme has T privacy and R reconstruction, that K is less than or equal to R minus T times L, and rho is less than 1. For computational efficiency, this refers to the computational complexity of the two algorithms defining the scheme of shared vector and reconstruction. Now I'll be discussing the construction from linear error correcting codes, or ECCs, and code split construction. This paper provides a new construction of secret sharing schemes from linear ECCs that has the advantage of assuring privacy for big sets of shares without requiring any specific properties from the duo of underlying codes. Let C be a linear code with parameter n, k, and d over the finite field f, and u be greater than or equal to 2, be a fixed integer. We will indicate with ENC an encoding algorithm of C. The new secret sharing scheme SHC and REC is defined as follows. To share m elements of the finite field to the power of k, first we have to compute the code V equals the encryption of m. Second, we have to share each component of V into U shares using the additive secret sharing scheme. Third, we have to define the shared vector as S from V1 element of n all the way to VU element of n. The encode split construction provides a way to construct efficient linear secret sharing schemes with explicit families of qualified and unqualified sets from generic error correcting codes. This is a high-level explanation of the constant rate construction. Let C be a KND code with generator G. Since G generates a code of distance D, if we remove D minus 1 columns from G, we still have a full rank matrix, rank K. This implies that if A is a subset of N is a set of cardinality D minus 1, then the map is shown is subjective. To define the scheme, we need to invert the aforementioned map. This inversion can be implemented easily if we assume that G equals the interval I to the kth element to M, where I to the kth element is K times K identity matrix. In this case, the sharing algorithm can sample x prime uniformly at random, then compute x double prime equals m minus x prime times m to the power of thou, and output x equals x double prime in a to x prime interval. Formally, giving a KND code with generator G equals the I to the kth element to m interval, I define a new secret sharing scheme via the following instruction. To share the message m, then compute x double prime equals m minus x prime times m to the power of thou, and output x equals x double prime in a to x prime interval. Formally, giving a KND code with generator G equals the I to the kth element to m interval, I define a new secret sharing scheme via the following instruction. To share the message m belonging to the finite field k, first you have to sample x prime uniformly at random and compute x double prime equals m minus x prime times m to the power of thou. And second, you have to define the vector x to the interval of x double prime to x prime and output it. Now I'll be discussing the security of secret sharing schemes, specifically the verifiables in a secret sharing scheme, or VSS. A VSS scheme is a secret sharing scheme where the dealer distributes shares of a secret to the parties P1 to Pn in such a way that the parties can perform some verification on the received shares. If the verification is successful, then the honest parties are guaranteed to get consistent shares of a well-defined secret or agree that the dealer cheated. In a VSS scheme, there's a strengthened reconstruction property. Each set, each set of honest shareholders qualified to reconstructs the same secret all the time. This paper discusses the new VSS scheme that can be based on the linear secret share scheme for which we know the relative n times m. The new VSS scheme uses the MSP notation to represent the underlying linear secret sharing scheme. This is a high-level definition of the VSS scheme. The dealer has a set of k secrets S1 to Sk in the finite field. He will then sample uniformly at random n times m matrix F with columns f to the power of I element of the finite field such that pi to the kth element times f to the power of I equals s to the ith element for any I equals 1 to k. Then, for any I equals 1 to n, the dealer computes the column vector and the row vector and sends them to a player. That player will send gth element times nth element to the thou to the rest of the players. Each players will check if they receive a valid value, and will broadcast accept if all checks are satisfied, and otherwise they'll broadcast reject. If all parties accept, then each player stores G I as a share, otherwise the protocol aborts. This slide will discuss the correctness and privacy of the new VSS. For correctness, if all n plus 1 parties are honest and follow the protocol, then the new VSS will not abort them. And for privacy, it is possible to prove that the joint distribution of the vectors doesn't depend on the secret shared. That is proved using the sweeping vectors corresponding to the sets 8 and simple linear algebra tools. The existence of the map that is shown below proves that all sets have the same size. Therefore, G to the ith element and I to the ith element have the same distribution for any sets of input secrets. Now for the mini-commit project commitment scheme. A commitment scheme is a cryptographic protocol between two parties, the sender and the receiver, consisting of two different phases, commit and open. In the commit phase, the sender commits their value while keeping it hidden from the receiver. In the open phase, the sender reveals M to the receiver, who can check that the revealed value corresponds to the committed one. Those two phases have to be implemented in such a way that the sender cannot change his committed value after the commit phase is concluded, and the receiver doesn't know the committed value until the open phase. The commit and open phase together form the online phase. Possibly before the online phase, there is a setup phase where the global parameters of the scheme are fixed. Let F be a finite field and K and N are positive integers. A commitment scheme for the values in the finite field is a two-party interactive protocol with the following phases: setup, commit, and open. In the setup phase, the input is an integer and the outputs are global parameters of the scheme that will be implicitly used in the commit and open phase. In the commit phase, on input M, which belongs to the finite field, a commitment C equals commit M and R, to which M is computed by the sender using a random coin R. The value C is sent to the receiver and stores it. In open phase, the sender simply reveals M and R to the receiver, and the receiver accepts the value if and only if the message corresponds to the committed value. Commitments are one of the most basic two-party primitive in cryptographic protocols, but it is nevertheless very powerful and important in both theories and practice to design many other cryptographic protocols. This is an example of the UC commitment from the ramp schemes. Assume that a sharing algorithm with the finite field K mapped to the finite field N of a scheme with T privacy R recognition, and a pseudo random generator where the set 0 to 1 to the L prime mapped to the finite field L are given. For the setup phase, PS will receive the sender's input and send them to the hybrid model. PR will receive the receiver's input and send those to the hybrid model. Then PR will receive the sender's input from the hybrid model. For the commit phase, to commit M elements to the finite field, PR samples randomness F and computes W. Then PS chooses an unused column Y to ether from the matrix Y defined in setup phase, compute the corresponding commitment message, and sends that combination to PR. PR will store that combination. In the open phase, to open the commitment number ether, PS will send the combination of the message and the randomness to PR. PR will then receive that combination of the message and randomness, compute W, and checks to see if W plus the unused column equals to the commitment message. If that check fails, PR will reject the opening and halt. Otherwise, PR will output accepts. When using the homomorphic UC commitment from the verifiable secret sharing scheme that I touched on earlier, the mini-commit project commitment schemes can either be additively homomorphic or multiplicative. If it is additively homomorphic, given C and C prime that are commitments respectively to M and M prime, then the sum C plus C prime is a commitment to M plus M prime. If it is multiplicative, given C, C prime, and C double prime that are commitments to respective M, M prime, and M double prime, multiplying C, C prime, and C double prime give us a value of 1 if M equals M prime times M double prime is 0 otherwise. The sender can prove to the receiver a multiplicative relation amongst committed values without opening values with the formula above. When using linear time UC commitment, the setup phase is modified to the one that was touched in previous slides. The modification ensures that the watchlist W is made only by indices corresponding to the one of the unqualified sets of the scheme linear error correcting codes. The receiver gets the U-1 Cs corresponding to its input set. The expanded strings are used to form the matrix Y, which are columns that are used to pad the share vectors as in the original linear time protocol. The commit phase and open phase are similar to the original protocol, with the only difference being that the sender and the receiver in this new protocol using the sharing algorithm from the linear ECC algorithm. Notice that the protocol is not homomorphic. Instead of constructing the commitment protocol directly from the sharing algorithm, it is constructed using the verifiable secret sharing protocol based on the scheme from the linear error correcting code. And since the linear error correcting code is not multiplicative, this new protocol commitment scheme is only additively homomorphic. The main goals of this PhD dissertation is to contribute to the state-of-the-art secret sharing scheme application and design, specifically a number of cryptographic primitives for whose construction secret sharing schemes can be fruitfully employed or identified in new secret sharing schemes with the properties required by the application or design. Two new constructions of homomorphic UC commitments are given. There's an input-independent setup phase based on an oblivious transfer. Then, and an online phase commitment are constructed using ad hoc secret sharing schemes and standard pseudo random generators. For the first one, the first construction is fully homomorphic and achieves a computational complexity of big O for the receiver and big OK plus epsilon for the sender. The second construction is only additively homomorphic but achieves a computational complexity of big O for both parties.